This is part 2 of the Year 13 AQA topic, acids, bases and buffers. There's a lot to think about in this particular video. We're going to introduce a lot of fairly straightforward calculations and there's lots of opportunity to practice them. Please do have a go at the activities, get to see what you can do and what you need to work on. So, in this video, we're going to look at what the term pH actually means. We're going to introduce the concept of logarithmic scales to people who maybe aren't so familiar. We're going to talk about how pH is measured, and we're going to use information such as pH to find out concentration of H plus and OH minus ions. So, definition of pH. What do we think? But there's lots of potential answers people could give. They might talk about it being the concentration of hydrogen. They might simply talk about the pH scale. But we now have a definition. This is what you'd write down as the definition, and this is what you're going to use in calculations. pH is negative log concentration of H plus, and it's log to the base 10. It's the log button on your calculator, so do find that because you're going to be using it a lot. Now, a logarithmic scale basically brings a very wide range of numbers into a narrower range of numbers. And I've got some information here about the Richter scale, which also operates on a logarithmic scale. We talk about an earthquake in Kent a few years ago that measured 4 on the Richter scale, not a huge amount of damage, and you can see the incredible impact in Honshu in Japan, which happened in 2011, Richter scale of 9. So just to get an idea, do you know what the difference would be in terms of the intensity of those earthquakes? It would actually be that Honshu was 100,000 times stronger than Kent, because every change of 1 on the Richter scale is an increase in intensity of 10. And that's the scale that we're going to be using when we come to pH. So do bear that in mind. So H plus and OH minus ions are generally very small. We'd be working with very fiddly numbers. Almost all pH values are positive. We are going to see that there are negative examples, which you won't have seen before A level. But what would be the simplest way to say what a difference of 1 on the pH scale would do to the concentration of H plus? And this is really following on from that Richter scale idea. For every time you increase or decrease your pH by 1, you are changing the concentration of H plus ions by a factor of 10. Okay, so we've got a question here relating to the pH of pure water. You're probably, if this is new to you, familiar with the idea that the pH of pure water is 7.00. That is true at 298K, but actually it isn't true at other temperatures. But let's see if we can prove that it's pH of 7 at 298K. So hopefully you've had a go there. Let's start with the expression for Kw from last video, H plus and OH minus. And if we've got a neutral solution, then we can actually assume that the concentration of H plus equals concentration of OH minus. We don't have an excess of either, which is what would actually take us away from neutral. So that means that we could rewrite Kw as H plus squared. And that further means that we can write H plus as root Kw. Now we know that Kw at 298K is 1 by 10 to the minus 14. So actually we can say that H plus is the square root of 1 by 10 to the minus 14 is 1 by 10 to the minus 7. Now earlier in this video we introduced the definition for pH. pH is negative log of the concentration of H plus. We know the concentration now, it's 1 by 10 to the minus 7. You crunch those numbers in your calculator and you get to a pH of 7. We've proven at 298K, water does have a pH of 7. But what happens at different temperatures? Try these 4 and then review. So on this one, my H plus is going to be square root of 0.114 by 10 to the negative 14, which gives me a value of 3.38 by 10 to the minus 8. If I substitute that into my pH expression, I actually get a pH of 7.47 for pure water if we do it at 273K. That's 0 Celsius, freezing point of water. Let's go across to the top one now, and again I've already done the rearrangement. H plus is the square root of my Kw value, and we see it comes to 8.25 by 10 to the minus 8. I substitute that into my pH expression, and that takes me this time to a pH of 7.47. 7.08. Temperature's gone up by 20 K there, not quite up to standard temperature, where we know it's 7.00. Let's increase the temperature again and try the next one. I substitute my figures in, I get to my H plus concentration of 1.72 by 10 to the minus 7, and what I then find when I put that into my pH expression, I'm summarising a little now so we can see the working out, we get to a pH of 6.76. And then I go on to the final example. I work out my H plus concentration in exactly the same way, 2.23 by 10 to the negative 7. I substitute that into my pH expression, and I get 6.64. So, a couple of questions for you to think about. What we can actually see is that we were increasing the temperature there, and the pH of pure water was actually going down. So, pH decreases as temperature increases for pure water. If it's not 7, why is it still neutral? Well, this is where we've got to rethink what we potentially think from lower down school. Because neutrality actually comes from the fact that H plus is equal to OH minus. Now we're going to move on and do a new calculation here. We're going to talk about calculating the pH of strong acids. And to begin with, let's deal with the definition. What is it that makes a strong acid a strong acid? And do we know any examples? Well, a strong acid is one that fully dissociates into its ions in solution. The examples that you're probably familiar with, HCl, HNO3 and H2SO4. So let's think about what that definition actually means. Every HCl will break down into H plus and Cl minus. HNO3 will break down into H plus and NO3 minus. H2SO4 will break down into 2H plus and SO4 2 minus. So we're talking about full dissociation of all of them for strong acids. The calculation itself, this talks you through the steps, and we're going to have a chance to practice these in a moment. I would always write out the expression for pH. I then substitute my concentration into that expression and then work out what the pH actually is. So I've got 6 questions for you to try here. See how you do. Well, my pH expression, negative log of the concentration of H plus, my concentration is 0.1, I put those figures in, that gives me a pH of 1. On the next one, I'm actually going to change what I write in my expression. Rather than 0.01, I'm going to put it into standard form, because there's something really important to see. pH is negative log of 1 times 10 to the negative 2, and the pH comes out as 2, the power or the negative of the power on my concentration. That will always be true when it's 1 by 10 to the negative x. We can prove that with the next one, which is 1 by 10 to the negative 3. pH comes out as 3. Then it gets a little bit more complicated. So we've got pH is negative log to the base 10 of 0.5. You substitute that into your calculator and you'll get a pH of 0.30. Now you might previously have thought of the pH scale going from 1 to 14. We're now seeing it goes lower. Next one, strong acid, and we have got a concentration of 0.004. So I substitute that in, 4 by 10 to the minus 3, giving me a value of 2.4. And again, we can look, is that in the right ballpark area? If it were 1 by 10 to the minus 3, we would expect the answer to be 3.00. It's reasonable then. 2.4 is not so far removed from there. And finally, we've got HNO3, a very concentrated one, 1.1. On this one, we get a pH of negative 0.04. Any acid where the H plus concentration is greater than 1 molar, the pH will be negative. So you do need to watch out for that. We're going to develop this further. Have a go at this question. So there is an extra consideration with sulfuric acid. It's a diprotic acid. My concentration is 0.02, which actually, when it dissociates into 2 H plus ions and an SO4 2 minus, means my H plus concentration is double. It's 0.04. I can now substitute that into my pH expression, negative log to the base 10 of 0.04, giving me a pH of 1.4. So let's put that into practice with 2 more examples. H2SO4, of 0.5 molar concentration means my H plus is 1 mole per decimeter cubed. Substitute that into my pH expression and I get a pH of 0. And on to the next one, I have got an H2SO4 concentration of 0.33 mole dm to the minus 3, so my H plus concentration is double that, 0.66. Substitute in to the pH expression and I get a pH of 0.18. So what we're now going to look at is the reverse of that reaction. What about if we're given pH but we want the concentration? Well, you can see that what we use here is often the second function on your log button on the calculator. Sometimes it's its own button. We want 10 to the negative x or 10 to the x. And when we put in these, we're going to do 10 to the negative pH. In this case, pH is 2. 10 to the negative 2 gives me a concentration of 1 by 10 to the minus 2. 6 examples to have a look at, see how you do. So, given a pH of 4.63, I'm doing 10 to the negative 4.63. That gives me an H plus concentration of 2.34 by 10 to the minus 5 mole dm to the minus 3. On to the next one, I've got a pH of 5.22, so I'm going to do 10 to the negative 5.22, giving me an H plus concentration of 6.03 by 10 to the minus 6. I'm now going to do the same with 10 to the negative 3.72, and that will give me a value of 1.91 by 10 to the minus 4 mole dm to the minus 3. We've got another acid here, HNO3, with a pH of 4.5, so 10 to the negative 4.5 gives me an H plus concentration of 3.16 by 10 to the minus 5. Nearly there with these examples. I've got H2SO4 with a pH of 1. So I take my pH is 10 to the negative 1, which gives me an H plus concentration of 0.1. But remember what we saw earlier with H2SO4. If my H plus concentration is 0.1, my H2SO4 concentration is going to be half that. So my H2SO4 is 0.05 mole dm to the minus 3. And a similar situation again here, my pH is 5.4, so 10 to the negative 5.4 gives me an H plus concentration of 3.98 by 10 to the minus 6, which gives me an H2SO4 concentration of 1.99 by 10 to the minus 6. We've got another new calculation, finding the pH of a strong base, but let's define what a strong alkali or strong base is. Well, it's very similar to what we saw with acids. They will fully dissociate in water. NaOH, every NaOH will break down into Na plus and OH minus ions. NaOH is the most common strong alkali, KOH also there as well. So with that in mind, I want you to have a go at working out the pH of 0.2 molar NaOH at 298K. And the fact you're given that temperature might actually be quite a good clue. So I'm actually going to start here with the ionic product of water. Kw is H plus times OH minus. I want the H plus concentration, so let's rearrange it. Now this is at 298K, so we know the ionic product of water is 1 by 10 to the minus 14, and we can divide by our OH minus concentration, 0.2, which takes us to an H plus concentration of 5 by 10 to the negative 14 moles per decimeter cubed. At this point, we can substitute that in to our pH expression, and that gives me a pH of 13.3. And we can ask ourselves, is that reasonable? Well, this is a strong alkali, a strong base. We would expect it to be on the far end of the pH scale, close to 14. So that seems entirely reasonable. So here's a model worked example taking us through a similar example with simpler numbers. If you want to pause this and have another look before you try some examples, just so you can get to grips with what it is we're trying to do, and when you're ready, move on to more questions. So we've got a couple of examples here for you to try. What are the pHs of these strong bases? Well, we've already done quite a lot here. So we've got the Kw, I've rearranged to make H plus the subject, and I'm working out H plus, Kw over concentration of OH minus. Remember, NaOH, strong bases, fully dissociate in solution. So if my NaOH is 0.5, my OH minus concentration is 0.5. Now I've got my H plus concentration, I can substitute that into my pH expression, giving me a pH of 13.7. And then we do the second example, 1 by 10 to the minus 14 over 0.003 gives me an H plus concentration of 3.33 by 10 to the negative 12. Substitute that into my pH expression, and that one will give me a pH of 11.47. And look, as it's getting more dilute, the pH is going down, closer to neutral, exactly as we would expect. But we have another calculation to consider, and this is finding concentration given pH, just like we did for acids, but it's slightly more complicated. Pause this, have a look at the worked example, and then try and put it into practice in the examples that follow. So, we've got 4 examples here. What's the concentration of a solution of NaOH with a pH of 8.5 at 298 K? Well, I want my H plus, which is 10 to the negative 8.5. So my H plus concentration is 3.16 by 10 to the minus 9. I actually want my OH minus concentration, so I'm going to rearrange the ionic product of water expression, Kw over H plus. And now I substitute the figures in. It's happening at 298K, so 1 by 10 to the minus 14 over 3.16 by 10 to the negative 9 gives me an OH minus concentration, and therefore NaOH concentration of 3.16 by 10 to the negative 6 mol dm to the minus 3. Let's try the next one, top right. H plus is 10 to the negative 14, that's 1 by 10 to the negative 14 as my concentration. My OH minus is therefore 1 by 10 to the negative 14 over 1 by 10 to the negative 14. I've got a concentration of 1 mole per decimeter cubed in that example. What's the concentration of a solution of NaOH with a pH of 7.5? Well, H plus is 10 to the negative 7.5. That gives me an H plus concentration of 3.16 by 10 to the negative 8. Substitute that into my rearranged expression for ionic product of water, and I get a concentration of 3.16 by 10 to the minus 7 mol dm to the minus 3. And my final example, pH is 10 to the negative 9.63. I've got my H plus concentration. I substitute that into my pH, into my Kw expression, and that will give me a value of 4.27 by 10 to the negative 5 mol dm to the minus 3. So we've got 4 new calculations there to try, to practice, to process, and to get confident with. That, however, brings us to the end of part 2. So thank you for listening, and goodbye.